in section 1.7, we're going to focus on linear inequalities and also absolute value inequalities. A linear inequality in the variable x is an expression that can be written in one of the following forms. Ax plus b is less than 0, ax plus b is less than or equal to 0, ax plus b is greater than 0, or ax plus b, have a typo here, so those are repeated. What do we have? We have less than or equal to, greater than, and this one should be greater than or equal to. So it's simply going to be an equality where you have the x to the first power and one of the four inequality symbols. To solve linear inequalities is pretty easy. You kind of want to do like what you would do with an equation, and that's get the x by itself. General rules, whatever you do to one side, you have to do to the other side. But with one very important additional rule, something we have to remember, and that's that if we ever have to multiply or divide both sides of the inequality by a negative, it changes the sign. For example, to kind of illustrate this property, we all know that the way that 3 compares to 5 is that 3 is less than 5, right? On the number line, here's 3, and 5 would be to the right. So when you're comparing two numbers, obviously the larger number, the one that's greater, would lie to the right. However, notice what happens if we compare the opposites of these numbers. If we compare negative 3 to negative 5, then on the number line, negative 3 is actually the one that lies to the right. So it would be the larger or the greater of the two. So notice, essentially, what would happen here is if I were to take this true statement, 3 is less than 5. And if I multiply both sides by a negative 1, we would get negative 3 and we would get negative 5. And notice what happens to the inequality. It changes direction. It changes from a less than to a greater than. Okay? So solving linear inequalities, the gist of it is it's just like solving general equations. You want to get the x by itself. But with this one special rule that if you either multiply or divide by a negative number, okay, only a negative, then you change the direction of the inequality. We can add and subtract to both sides. That won't change anything. We can multiply and divide by positives. That won't change anything. It's simply multiplication and division by negative numbers that changes the direction of the inequality. Typically, whenever we solve these, there's three different forms we can put the solution in. We can put it in solved interval notation, solved inequality notation, where we have the x by itself. We can also graph the set, so we can graph it on a number line. And then we can also express the set in interval notation. So I'll do the next couple and we'll show the solution set in each of those three different ways. For example, one we're asked to solve. We also want to graph and express in interval notation. The first step we want to do here to get the x by itself is we're going to go ahead and add 5 to both sides. That would give us 3x is greater than negative 12. The next step to get x by itself is we would need to divide both sides by 3. Notice that we're dividing by a positive 3, so that's going to keep the inequality going in the same direction. And we would get that x is greater than negative 4. So as a solved inequality, any value of x that's strictly greater than 4 would be a solution. We can also now graph this. Let's show what the graph would look like on an interval. Here's 0, negative 1, negative 2. This should be equally spaced. Negative 3, negative 4 is over here. Because it's greater than means go to the right. So I'm going to shade the portion of this that is greater than negative 4. So that's going to be everything to the right. And also notice here that because it's a strict inequality, meaning we're not actually able to be equal to negative 4, then this negative 4 point will not be included. To demonstrate that, we can either use an open circle like we have here, or some people will use a soft and a rounded parenthesis to indicate that as well. So you can either use open circle or a parenthesis for that. If it had been included, if it had been greater than or equal to, then we would be using a filled-in circle at the point, and then that particular endpoint would get a bracket. Okay. Last but not least, we want to show our solution in interval notation. Typically, if you have the graph first, the graph makes it very easy to list it in interval notation. Always go from left to right. The leftmost value is negative 4, which is not included, so that gets a parenthesis. and it goes all the way to the right towards positive infinity, and infinities are always parentheses, so it should look like this. So this is our solution set displayed three different ways. The first way is a solved inequality. We also can graph our solution set, and in part C we've shown the solution set in interval notation. Typically on an exam I will ask for all three of these, just like what we did for example 1. Let's take a look at the next one. We want to solve, and we're also going to graph and do interval notation for this. To get the x by itself, the first thing we would do is add 4 to both sides. We would get negative 2x is greater than 10. The next step to get x by itself is we need to divide both sides by negative 2, and this is the thing that we have to be on the lookout for. Because we are dividing both sides by a negative, that's going to change the direction of the inequality. So instead of having a greater than, we're now going to have a less than. We get x is less than negative 5. So the solved inequality is x is less than negative 5. We can go ahead and graph this. You don't have to plot all of the numbers, but somewhere on the number line, you're going to have negative 5. Less than means go to the left, and once again, it's not going to be included. So you can either do a open circle like this, or if you prefer, you could even do it with a parenthesis. Lastly, we want to give our solution set in interval notation. Always go from left to right first. This shaded region goes all the way to the left towards negative infinity, and it goes up to right up to negative 5, which is not included. Okay. So there is our solution set. X is less than negative 5, which would look like this graph, and this is it in interval notation. The next style of inequality we're going to look at is what's called a compound inequality, and this is formed by joining two inequalities with the word and. For example, we might have a situation where we want the quantity 2x plus 1 to be greater than negative 3, but we also might need that for that same quantity 2x plus 1 to also be less than or equal to positive 3. We can combine these two separate inequalities into a single compound inequality like this. In this compound inequality, we have two inequality symbols with a part to the left, the middle part, and then the right part. It's almost kind of like if you were to compare three real numbers. You'd have, in this case, because of the direction of the inequality, this would be the smallest, this would be the middle or in-between quantity, and this would be the largest quantity. Typically, to solve these, you follow the same general rules, except this time, because we have three pieces, whatever you do to one piece, you have to do to all three pieces. And once again, if you multiply or divide by a negative, we have to switch the directions of all of our inequalities. Let's go ahead and solve the first one. We want to solve negative 3 is less than 2x plus 1 is less than or equal to positive 3. Notice that the x variable is in the middle here. So that's where our attention and focus should be. To get x by itself, we're going to need to subtract 1. But if I do it to the middle part, we have to do it to all three parts. Negative 3 minus 1 is negative 4, is less than, we're going to get 2x, is less than or equal to positive 2. And then the very next step would be to divide everything by 2, divide by 2, divide by 2. We get negative 2 is less than x, is less than or equal to positive 1. Notice that we're dividing by a positive number, so that is not going to change the direction of the inequality. To graph this, notice that we have two real numbers. So here's 0, negative 1, negative 2 would be here. Positive 1 would be over here. And if we look at it, how x is sandwiched in between, we're going to be shading the part of the real line that's in between those two numbers. First of all, notice that the negative 2 is strictly less than x, so the negative 2 will not be included, whereas the positive 1 will because it's less than or equal to, like this, and then simply shade everything in between. For those of you that want to use, parentheses and brackets, it would be parenthesis, graphed, and then over here you have a bracket. We can now write this set in interval notation. Always go from left to right. The shaded region goes as far to the left as -2, which is not included, so that gets a parenthesis. It goes as far to the right as +1, which is included, so that will get a bracket. So we've now solved this compound inequality. We solved it for x, we graphed it, and we also wrote our solution set in interval notation. The last type of inequality we're going to look at in this section is what's called absolute value inequalities. And they come in two different types. We could have types of the form the absolute value of u is less than c, where c is a positive number. This is simply saying that the expression u has to be within c units of 0. In other words, this would mean that u would have to be between -c and +c. We call this an absolute value inequality of the first type. Alternatively, if it's of the form the absolute value of u is greater than c, this would mean that the quantity u has to be more than c units from 0, which means that u has to be either less than -c or greater than +c. And the same would hold true if we allow for these to be either less than or equal to or even greater than or equal to. The first step in solving these types of absolute value inequalities is to first of all isolate the absolute value. You want to get the absolute value on one side of the equation and everything else to the other side. The next thing you would want to do is to recognize which of the following two forms it is, because that's going to indicate the type of setup that we do. If it's u an absolute value less than c, then we can form the compound inequality -c is less than u is less than +c. If it's an absolute value inequality of the form absolute value of u is greater than c, then we have to form two disjoint inequalities. The first one is u is less than -c, or u is greater than +c. Let's take a look at the first one. We're asked to solve, and we're going to graph and do interval notation for this as well. The first step is already done for us. We have the absolute value by itself. So we now look at the type that we have. It's absolute value less than a number. So this would be like our first type. To set it up, what we're going to do is we're going to take that x minus 4. We set it equal to 3, but then we also have to simultaneously set it greater than the -3. Once we're here, it's a compound inequality. We solve this like we did the last couple. We want to get x by itself, so we're going to add 4, which means we need to add 4 to each of the three pieces. This will give us +1 is less than x is less than 7. We've got the x by itself, so this would be our solved inequality. If we wanted to go ahead and graph this, here's our number line. Somewhere on there is 1 and 7. These are both strict inequalities, so neither number is included. And then we would shade everything in between because x is in between those two values. From the graph, having that first makes it easier to do the interval notation. From left to right, this shaded region goes as far to the left as 1, which is not included, and goes as far to the right as 7, which also is not included. So there's our solution set. Solved inequality, graphed inequality, graphed interval, and interval notation. Let's take a look at example 6. Here we want to solve and graph the solution and express it in interval notation. First thing we need to do here is we need to get the absolute value expression by itself. So we want to solve for the absolute value quantity. To do that, we're going to first subtract 7 from both sides. So subtract 7, we get -2, absolute value of 3x plus 5 is going to be greater than or equal to -13 minus 7 will give us -20. The next step to get the absolute value by itself is we now need to divide both sides by -2. Keeping in mind that dividing by that negative, that's going to change the direction of the inequality. So instead of having a greater than or equal to, this now becomes a less than or equal to. We have 3x plus 5 in absolute value is less than or equal to +10. With the absolute value now by itself, we recognize that this is an inequality of type 1. So we take the 3x plus 5, we set it less than or equal to positive 10, and simultaneously greater than or equal to negative 10. To solve this for x, we would now begin by subtracting 5 from all three parts. We get negative 15 is less than or equal to 3x is less than or equal to positive 5. And then the very next step is to divide everything by 3. We're dividing by a positive 3, so that's not going to change any directions. We get negative 5 is less than or equal to x, which is less than or equal to 5/3. To finish this off, let's now graph it. On the number line, negative 5 is somewhere to the left of 0. Here we have positive 5/3, which would be the same thing as 1 2/3. Because we have less than or equal to, those endpoints will be included because of the equality component. So those would be included, and then we're going to shade everything in between. Again, if you were to do parentheses or brackets, that means that that shaded region would have brackets on both ends. For the interval notation, always from left to right, this shaded region goes as far to the left as negative 5, which is included, and goes all the way to the right to positive 5/3, which is also included. So that's our detailed solution set for this one. Let's take a look at example 7. We want to solve 7 is less than 5 minus 2x in absolute value. The absolute value is already by itself, and notice that this is essentially saying that the absolute value is greater than some number. In order to solve this, what we're going to do is we're going to take the part on the inside, the 5 minus 2x. This either has to be greater than 7. So we set 7 less than 5 minus 2x. Or we could have negative 7, the opposite, is greater than 5 minus 2x. So one of the ways that sometimes I feel like oftentimes will help students when you're trying to set up the absolute value inequality of the second type is one of the things you do is one inequality is simply formed by just dropping the absolute value bars. The second one is formed by changing the sign of the real number and the direction of the inequality and setting it equal to the thing in the absolute value bars. From here, we want to go ahead and solve this. We can subtract 5 from both sides. We get 2 is less than negative 2x. Now to get the x by itself, we have to divide both sides by negative 2. Divide both sides by negative 2. Remember, that's going to change the direction of the inequality. So we have negative 1. This will change now to a greater than x. Okay. Over here, it's going to be the same work. We need to subtract 5 from both sides. We get negative 12 is greater than negative 2x. We're now going to go ahead and divide both sides by negative 2. Dividing by a negative changes the direction, so we're going to get a positive 6 will be less than x. So we have our solved inequalities here. It's negative 1 is greater than x, or 6 is less than x. For the next part, when we ultimately go onto the graph and when we try to do the interval notation, it's sometimes more difficult for students to do that when the x is on the right-hand side of the inequality. You can rewrite this, and I find this to be very helpful. Notice if you look at the way it compares between negative 1 and x is the smaller value because negative 1 is greater. So if you kind of rewrite it, some people remember like the analogy, the alligator mouth always eats the bigger number. So if you flip-flop the values of x and negative 1, if you change their positions, notice that the inequality should still open up towards the negative 1. It's like saying the same type of relationship, but in two different ways. We can say that negative 1 is greater than x, means exactly the same thing as saying that x is less than negative 1. Similarly, if we come over here, we could also say that x would be greater than 6. So this is our solved inequality. We're now going to go ahead and graph this. We have two numbers. We have negative 1 and we have 6. The first inequality says that x is less than -1. So that's going to be everything to the left, and it's not included. X is greater than 6 would be everything to the right, which again is not included. And so in this type of inequality, the absolute value inequality of type 2, we actually get two disjoint unions of intervals. The first part is everything from -infinity up to but not including -1. We also get this interval here, which is from 6 to +infinity, where the 6 is not included. And then to demonstrate the whole solution set, we oftentimes put the u in between to say that it's the union of the two. It's this piece or that piece. We have one more to look at. Let's take a look at example 8. Once again, to get started, we want to get the absolute value by itself. So we're going to divide both sides by -2. Dividing by a negative is going to change the direction of the inequality. So we now have the less than turns into a greater than. -6 divided by -2 is going to be +3. We have absolute value greater than. This is our type 2. So we take the x minus 1, set it greater than 3. Or we take the x minus 1 and set it less than the negative of 3. Let's go ahead and solve each one. This one will give us x is greater than 4, add 1, or we get that x is less than, it's supposed to be a plus 1, x is less than -2. We can graph this. Here's our number line, -2 and 4. The first inequality says that x is greater than 4, so greater than means go to the right, and that's not included. Less than -2 would be everything over here, like this. We now have our graphed interval. Now we're going to do interval notation. We have two distinct separate intervals. The first one is from -infinity to -2, union from 4 to +infinity. So we've solved this absolute value inequality. We're going to finish with two special types, and just something you kind of have to be on the lookout for. If we go back to when we described how to solving these two types of absolute value inequalities, we had this condition that c is a positive number. Okay. If you're not paying attention to this, you can very easily miss some special cases that might happen. For example, in 9 part A, we have the statement that the absolute value of x plus 3 is less than -6. So while it does look like an absolute value inequality of type 1, if you just think about the way in which absolute value works, when you plug in a number into an absolute value, the smallest output you could ever get would be 0 if you have the absolute value of 0 itself. Other than that, the absolute value of any real number is going to be a positive quantity, and therefore it would be impossible for it to ever be less than -6. That can't happen. So the equation in 9a, that one would actually have no solution. And again, the reason for that is because absolute value can never be less than a negative number. Similarly, if we look at b, we have the absolute value of x minus 7 is greater than or equal to a negative. That will always happen, right? Absolute value will always be at least 0 or greater. So certainly this will always be bigger than the -9, which means that our solution set is going to be all real numbers. So you can write the stylized R symbol for the real numbers. You can use the word all reals. But this is something we can actually graph because we do have a solution set. Simply put, we're going to get the entire real line. So every real number in this case is going to work. And the way that we write the real numbers in interval notation is it's everything to the left and then everything to the right, which is from -infinity to +infinity. So as you're working through your setups on these, just be on the lookout. If you end up with absolute value compared to a negative quantity, it'll either be no solution or all real numbers depending upon the direction in which the inequality faces.